for this practical, you have to make up 2 stock solutions of the 2 buffer components. And we said for a buffer, we usually have an acid and a base. And I'll come back to that in a minute. So you have to make up the stock solutions for that. The 2 buffer components. You then mix the 2 stock solutions and to make a buffer with a desired pH. And you also use the Henderson-Hasselbalch equation to check whether your calculation was right. And what you will find is that your calculation wasn't right. But that's perfectly okay, and we will discuss that, why this is, in the post-lab session on Friday. You will also investigate what happens when you dilute a buffer. And you might find this slightly surprising, what happens, i.e. nothing. And then the second part of this practical is where you will titrate phosphoric acid with, I think it is sodium hydroxide or something like that. And the cool thing about phosphoric acid is that this particular acid can give off 3 protons. It is H3PO4. And it can give off 3 protons, as I said. And you will see when you titrate it, what happens actually with this acid. Something really weird happens. The learning outcome for tomorrow is that you understand how to use a pH electrode, and we will show you that, how you deal with that. So our demonstrators will show you the do's and the don'ts. These things are fairly expensive, so I would advise you not to break it. It's about 200 quid a pop. And that can be a little bit cumbersome when we have to replace it. So please don't break it. So for the first question that you have to do, you have to make up a stock solution of buffer components. And we use 2 components. One is this guy here, potassium dihydrogen phosphate, and the other one is disodium hydrogen phosphate. So these are the 2 components that we use, and they are acid and conjugate base pair. Now, they look really weird, don't they? Which one is the acid, which one is the base? What do you reckon? Which one is the acid, which one is the base? What's the characteristic of an acid? Loud? It gives away, not hydrogen, but protons. Yeah? It gives away protons. So, the acid has definitely more protons than the base. And with this knowledge, you can immediately identify which one is the acid. It's this guy here. Yeah, because it has 2 protons in it, whereas the disodium has only 1 proton. So this one here would be the base. And they are conjugated because the acid just simply has 1 proton more than the base. We can, in a way, we can completely ignore the counter ions here. And we can say what we have here is H2PO4 minus, and here we have HPO4 2 minus. Yeah? if that's more familiar. So you see the acid has 1 proton more than the base. Happy with that? So the task is make up 50 milliliter of 150 millimolar solution and here are the molecular masses. So let me just quickly rewrite that again, because when it is sometimes in such a wordy form, then things easily get lost. So what we need to do, or the task is, make up 50 milliliter of 150 millimolar solution of acid, and the molecular mass was 136.09. You see here it doesn't have a unit. It just simply says the MR, the relative molecular mass is. So what you need to do is when you see something like that, you just simply have to think that it's gram per mole. So we have 136.09 gram per mole. So that's the task. I give you 2 3/4 minutes to work out for yourself how you would attack this problem. You can talk to each other, work in groups. So try to figure out how you get this. Okay, let's do it together. What's the unit of the stuff that we are looking for? Grams. Do we have grams anywhere? Yes, indeed. We have 136.09 gram per mole. Now the gram is good, but we need to get rid of the mole. So we multiply it so that the moles cancel out. Do we have anything with mole? Where? 150 millimolar. That means 150 times 10 to the minus 3, that's the milli, mole per liter. Yeah? Now the moles cancel out, but we've got the pesky liters, so we have to multiply it in such a way that the liters cancel out. So that would be 50 milliliters times 50 times 10 to the minus 3 liters. Now the liters cancel out. And all we have to do is really 136.09 grams times 150 times 10 to the minus 3 times 50 times 10 to the minus 3. And if you've done that properly, you get 1.02 grams. So you would need 1.02 grams of the acid in order to make up this solution, 50 milliliter of 150 millimolar acid solution. So that's what it says here. And now you've done that, you can also immediately calculate how much of the base you need. Again, with the base, you need to make up 50 milliliter of 150 millimolar solution base. And the base has a molecular mass of, what was it again? 142.1. 142.1 gram per mole. Okay? Over to you. You have seen now how it's done. Calculate how much you need for that. So if you get 1.06 or so, 1.07, yeah, rounded, gram for the base, give yourself or somebody else a pat on the shoulder. Well done. This is not an invitation to groping, yeah? Just want to point that out. Okay, so the way you make up these two components is you add them. It's best practice to first dissolve them in a beaker with 40 milliliter of distilled water. Make sure that the salts are completely dissolved, and then you add it up to 50 milliliter in a volumetric flask. We give you these flasks. Make sure that the meniscus is in the right place, right? So, and make sure that everything has gone into solution. So these are your stock solutions, and we want you to measure the pH of these stock solutions. So if you look at the acid here, you obviously would expect a pH higher or lower than 7? Lower. So it must be smaller than 7. If you use a pH, if you use the base, it should be higher than 7. So that was the first task. Let's see what else we need to do. You then take the two stock solutions, you take the acid, and you use 25 milliliters of this acid solution in a beaker, and a magnetic flea, that's the stir fleas. Have you worked with them before? Yeah, okay. Please don't try to make them levitate by turning up the magnetic stirrer so fast that they start coming out of the beaker. That's sometimes quite spectacular when it takes off. It's a helicopter flea. Please don't do that. So what you need to do in this case is measure the pH and then slowly add different amounts of different milliliters of the base here. And I would assume that probably a good way of doing that is add the 150 at the base in 0.5 milliliter steps. And what I want you to do is add the base, 0.5 milliliter, check the pH, record the pH. Record how much of the base you added. Okay? So, 0.5 milliliter, pH is 5.3. 1 milliliter in total added, pH, Another 1.5 milliliter added, pH, until you reach a pH of 6.5. And I want you to then check out how much of the base you have actually added at that point. Okay? Happy with that? Sounds pretty straightforward. So one person can add the base and the other one can record pH. Okay, what else have we got to do next? Nope, that's not what I want. Okay, so the next step then is we're using the Henderson-Hasselbalch equation. Now here in your manual it is written as pH equals pKa plus log base over acid. The same thing would be pH equals pKa minus log of the acid over base. It's just slightly, it's sort of the other way around, but it means exactly the same. Mathematically, it is exactly the same. Okay, so what does it say? What we need to do? We need to calculate, in this case, if we want to have a buffer of 6.5, we need to calculate our acid to base ratio. So, we have the pH, which should be 6.5. We know that the pKa is 7.2 for this acid-base system. We know our Henderson-Hasselbalch equation, pH equals pKa minus log of acid over base. Now, what we want is calculate acid over base ratio. Before you get started with these things, I want you to do what I call reality check. This means, let's not get the calculator out, let's try to think about this problem and what we would expect. We have a pH of 6.5 and the pKa is higher than that. What does that mean? Do we need more acid or do we need more base? I've heard it. Yes, you're absolutely right. But somebody else? Do we need more acid or base? We need more acid. If pH is lower than pKa, more acid. If pH is higher than the pKa, we need more base. And if the pH is the same as the pK, equal amounts. Yeah? So in this case, we need more acid. Okay, so can we calculate the acid to base ratio from the given things? Over to you guys. Try your luck. Okay, so did anyone get anything meaningful? What did you get? Don't hit him. He's only little. What did you get? 5.01. 5.01, aha. Now the big... Did anyone else get 5.01? Hands up. Okay, did anyone get anything else? Don't you elbow her, right? Oh yeah. Don't want you to connect. Okay, let's do that together, right? Because that is a question that will, under guarantee, will bite you in an exam or in a test. Right? So, we want to calculate the acid-base ratio. How are we going to do that? First of all, we bring the log part to one side and the pH to the other side. So this goes to that side, this goes to that side, yeah? And it's just simply rearranging an equation. So we have log acid over base that goes with plus to the other side equals pKa minus pH. So the pH goes to the right-hand side. Yeah? Just simply rearranging. Now we can put in numbers. Equals pKa is 7.2 minus 6.5, and if my fingers are not mistaken, this gives us 0.7, right? So, I don't want to know the log of the ratio, I want to know the ratio. So what I do is, I do the inverse operation of log, which is 10 to the power. So I do 10 to the power of, and I get 10 to the power of log acid to base. And I have to do that with both sides of the equation, equals 10 to the power of 0.7. 10 and log, in this case, cancel out. And we have acid to base ratio equals 10 to the power of 0.7, I don't need a calculator for that, is 5. I'm a very sad person. I used to learn my logarithms. I was pretty good at that at one point. So if you really don't have anything else to do, you know, this is good memory tests for you. So what does that mean? It means we have 5 times more acid than we have base. Does that actually make sense? Let's go back. We said if the pH is lower than the pKa, we need more acid. Now we say we need 5 times more acid than we need base. It makes sense. This is sort of a reality check. That's always good. Now this 5, what does that actually indicate? Well, we need 5 parts acid for each 1 part base. I can write 5 as 5 over 1. Yeah? Make sense? So, in order to get this buffer of 6.5, we should, in theory, mix 5 parts of the acid with 1 part of base. So you could, for example, use, let's say, 10 milliliter of acid. You add 2 milliliter of base, and then you check the pH of that. In theory, it should be 6.5. If you do it tomorrow, you will find it's not 6.5. Right? Why this is, we will discuss on Friday. You happy with that so far? Ha, fantastic. And the last bit. Oh yeah, you then have to dilute some of the buffer as well that you made. And I want you to check out, as it says in your practical, check out what happens to the pH. Will the pH change? Will it not change? Again, we will discuss the result on Friday in the post-lab discussion. Lastly, I want you to do this titration experiment where you use the H3PO4 can give off 3 protons, and you add sodium hydroxide solution. And I want you then to graph, on graph paper, what's going to happen, how the pH changes when you add the sodium hydroxide solution, let's say half a milliliter, or does it say? No, 0.1 milliliter, 100 microliter, in, stir, read the pH. Next 0.1 milliliter of the sodium hydroxide, stir, read the pH. Yeah? And I want you to see what's going to happen with the pH. It will do something really weird. I want to know from you why it's doing that on Friday. Okay? Happy with that? So in theory, this practical should be fairly quick. I would suggest, because I don't know how many pH meters and how many balances we have, that some couples, because you're working in pairs as far as I understand, some groups start with the titration here. Then they are not in the way of people who are weighing in things, and then we swap over. But I leave that up to you to organize it. Okay? Happy with that? So you can do it? Bob the Builder or Barack Obama? Fantastic.